So here we will discuss about traveling salesman problem. So there is a salesman, or let's say a postman, who's going on flight and he has to deliver letters at all the cities and come back. So let's say there are flights from various places like this also. These are flights and I can go from any place to any place, but the flight tickets are different for different pair of cities. So now I have to choose some cycle or some way of traveling so that my cost is minimized. I start from New Delhi. I cover all the cities: Kanpur, Bhopal, Kolkata, Bangalore, Mumbai, and then come back to New Delhi. So which path or which cycle should I take so that it's of minimum cost? So this is the idea, a problem which is quite simple, but the solution we will see is not that simple. So in graph theory we can represent it as, let GVE, so given a graph with vertices and edges, and it's a directed graph. Okay, so it's a directed graph with edge cost given by Cij, which is 0 when the node goes from itself and to itself, and it is some finite value, and if two cities are not connected or two nodes are not connected, then Cij is equal to infinity. Okay, so a tour of the graph is a directed simple cycle that includes every vertex in V. Okay, so it includes all the vertices exactly once, and it is a simple cycle, and the cost of the tour is sum of the weights of the edges of that tour, and TSP is the minimum cost tour. Okay, so this is the idea how to solve it. So we see it's basically how we are covering, if we have n cities or n nodes, so we have to travel all the nodes, isn't it? So we have to travel all the nodes and then come back. So we see this is not choosing some subsets out of some n elements like we have seen in different problems like knapsack problem or something like that, but here we have this is a permutation problem. So this is a permutation problem where we have to try out all different permutations. So let's see. So we have a 4 node graph. So if I'm making a cycle, so cycle will have what? It will have all the cities. So I know that, okay, it will contain all the nodes. So it is a kind of permutation. So I can have 1, 2, 3, 4, 1, 2, 4, 3, etc. But what happens is that cycle, so I can take, let's say I always start from node 1 without any loss of generality, I can say. So what happens now, n minus 1 cities which I have, I can arrange them in n minus 1 factorial ways. So these are the ways in which I can go from like 1 to 2, 2 to 3, 3 to 4 and back to 1, or for these 4 cities I can go 1, 2, 4, 3, 1, 1, then 3, then 2, then 4, then 1, 1, 3, 4, 2, 1, 4, 3, 2 and 1, 4, 2, 3. So there are 6 possible ways, which is 3 factorial. Okay, so we see that, okay, now this is a permutation problem, and which is n factorial is O of n to the power of n. So it is even more harder than the selection problem. And so what is the brute force algorithm for it? We will try out all n minus 1 factorial cycles, and we will first find whichever are feasible. So it might happen that in many cases like edge 2 to 4 doesn't exist, so I cannot take this cycle. So whichever are feasible, I will find the minimum cycle among the feasible solutions. So to decrease the complexity, we use dynamic programming. Okay, so again, as I said, without any loss of generality, in a cycle I can start from anywhere, it doesn't differentiate. So let's say I start from vertex 1 and each tour consists of an edge. So what happens now, let's say that each tour consists of an edge. If I start from 1, so it will next go to some other node, so that is one edge 1 to k, and that k belongs to all the set of vertices minus node 1, and a path from vertex k to vertex 1 which goes through all the vertices in v minus 1 comma k, and it goes through all of them exactly once. Okay, so it says that, okay, if we have a graph, so what happens? So it goes like this. So let's see, we have a graph, and so this is node 1, 2, 3, 4, 5 and 6. So let's say if it goes through node 2, which is k, let's say k is 2, then what happens? Then it will go through the path will go through all other nodes 3, 4, 6 and 5, and then finally to 1. So it consists of two parts. First is the edge from 1 to k, then a path from k to 1, which consists of all vertices in the graph except 1 and k. So if the tour is optimal, then path from k to 1 through all the vertices in v minus 1 comma k should be shortest. So this is the optimality, that okay, if I am going through first edge and then going through all the nodes in the graph, then the sum of them should be the smallest. So this is principle of on optimality. And so now let's try to formulate the problem. So let's define GIS is equal to length of shortest path from node I. So I have a path from node I and going through all the vertices in set S and then terminating at 1. So this is quite interesting. So let's try to understand this variable. So G I comma S. So I is a node, S is a set of vertices in the graph. Okay, so what we have to do, so 1, then we have some vertices, so this is the vertices 1, and then we have like vertex I here, and all other vertices are there. Then what happens is, so GIS means what? There the length of the shortest path which starts from node I and it goes through all the vertices. So let the S be these yellow vertices belong to the set S. Then GIS means what? So it starts at node I, the path, and it goes through all the vertices in this set. So let's see like this, and then it terminates at 1. So this is the meaning of GIS, and it is the length of the shortest path in the yellow line. Okay, so this is GIS. So now let's see what happens. So if I give G1 comma V minus 1, it is the optimal length tour. So this gives me the tour because I start from node 1, then I go through all the nodes in the graph except node 1, that path, and it comes back to 1. So this is the path and it comes back to 1. So now let's see. So G1 comma V minus 1, as we told, it consists of one edge, which is the first edge from 1 to some node k, and then it consists of a path from k to 1, and it consists of all the nodes in the graph except node 1 comma k. So let's try to again see with one graph simple example. So if we see, this is 1, and let's say this is, so 2, 3, 4, 5 and 6, and we make some random graph. Okay, so not this one. Okay, so we can add one more, so 7. So what happens now? So let's see. So what I'm saying is, so G1 to, so if there is a tour, shortest tour, so it starts at, let's say 1, and we choose a k, that okay, the optimal tour, it goes from 1 to, let's say 2. So then this is fixed now, and then what happens? So it goes from 1 to 2, and then it will follow a path which will consist of all nodes in the graph except 1 and 2. So it consists of 3, 4, 5, 6 and 7, and then it goes back to 1. So this is what is the meaning. So what we do is that this is the summation, and I can choose the path k, the node k from 1, where the cycle will go from 1 to some other node. So that can be anything from 2 to node n. So it can be 2, 3, 4, 5, 6, 7. So I will try to find the minimum among all of them, for which this summation c1 to k plus the sum of the path from that node k to node 1 with the set of nodes that are covered is v minus 1 comma k. So I hope it's clear. And then what happens is, and now we can generalize. So GIS that we had defined, like a path starting at node I, covering all the nodes in set S and going back to 1. So we define it as, so minimum of Cij. So I go to some node in the set S, and then I went to node J, and then from there I start another path at node J. It covers all the nodes in set S minus J and goes back to 1. So this is something like generalization of this equation, and then we use this to solve the problem. Our problem is G1 comma V minus 1 we try to solve, and because this is the biggest problem, to solve this we use some sub problems which are of the form G k comma V minus 1 comma k for all choices of k. Okay, so we will see this with an example. Okay, so that will be much easier. This till now we have followed, we have got something in our mind, and with the example we will make it more clear. So let's see. So this is a graph, again representing a directed edge graph was a little cumbersome, so I use this one. So this is a graph which means from node, this is node vertex 1, this is vertex 2, this is vertex 3, this is vertex 4. Here it means like 1 comma 3 means going from node 1 to node 3 is cost is 15, going from node 3 to node 1 is of cost 6, something like that. So all these costs are given. So now let's see. So we have G, and I say that okay, I go from bottom up, I calculate Gi comma S for S of all sizes from 0 to n minus 1. Okay, so G of I comma phi means what? I start from node I and end at node 1 with no other vertices in the set. So it means what? I start from node I and terminate at node 1 without any other node. So this is directly an edge, so it will become equal to C of I comma 1. Okay, so we can calculate G2 comma phi. So we start, so 2 comma phi means what? I start from node 2, I end at node 1, so it will be C21, and C21 is 5 here. Similarly G3 comma phi is I start from node 3 and end at node 1 with no intermediate vertices in the path, so it is C31, and C31 is 6. So this is for mod S is equal to 0, no set nodes in the set. So G4 comma phi is C41, similarly it is 8. Okay, so now we calculate for mod S is equal to 1, so one node in the set. So I start with 2. Okay, so because 1 we are already starting from 1, so we don't calculate for 1. So G2 comma, so I have now, I can have set of size 1 which can be, I can have node 3 and node 4, isn't it, for node 2, because I am already going to node 1, so I don't have that in the set. So G2 comma set is 3, so it will be, now what we see the formula. So GIS is minimum of Cij plus G of j comma S minus j. So S is the set of all vertices and I subtract j from that. So let's see. So here our set was only one node 3, and so it will be Gi comma S, so it will be C so I choose one j here, which is 3, so c2 comma 3 plus g3, and from that set I have already subtracted 3, so it becomes 5. So it is c23 plus g3 comma 5. So g3 comma 5 I have already calculated, so it's here. So it is 9 plus 6, 15. Okay. So similarly g2 comma 4, it means what? I am starting at node 2 and I will follow a path which terminates at 1 and it goes through node 4. So this will be what? So it will be, so because there is only one node, so it will go through that, only one possibility. So from 2 it will directly go to 4, so it will be c2 comma 4 plus it will be some path from node 4 to node 1 which has no other nodes in the path. So it will be g4 comma 5. So this is c24 plus g4 comma 5, which was already calculated at 8. So it is 18. So similarly we calculate g32, g34 and g4 2, g4 3. So what we see here is, for each of the numbers I calculate the mod s is equal to 1 subset and try it out. So now I have calculated for mod s is equal to 1. So here there were, count was 3 here, and here the count is now 1 2 3 4 5 6. So here the count is 6. And now what happens, I will try now, because I have already got the subset size 0 and 1, I will calculate subsets of size 2. I don't include node 1 again because it is already, the path is starting from there. So g2 comma, so subset size is 2, so it will be 3 comma 4. So now it means what? I am going from node 2, I am starting from node 2, I have to have a path which covers node 3 and 4 and it will end at node 1. So what happens, I have now two possibilities. One is I go from node 2 to node 3 and then get to 4, and other one is I go from node 2 to node 4 first and then node 3 and then 1. So here what happens, it will be minimum c23 plus g3 comma 4, which means I went to node 3 first and then I took a path afterwards, and here it means c24 I went from 2 to 4 and then from 4 I went to 1 with using node 3 in the path. So I calculated these, so it is 9 plus 20, 27, and this is 25. So similarly I calculate g3 comma 2 comma 4, g4 2 3. So I calculate it to be 25 and 23, and finally let's see, we calculate g1 2 3 4, which is the optimal tour path calculation. So here what happens, again we see here, from 1 a path can go to node 2, all different cycles. So first cycle we might have from 1 to 2 we might go, and then some other path from 2 to all other nodes. So this is here c1 2 I take, and I say from 2 I again go through node 1 finally, but taking 3 and 4 in the path. So this is this one, which comes out to be 35. Then other way is like I go from node 1 to node 3 and then from node 3 to node 1 with node 2 and node 4 in the path, which comes out to be 40. And last option is I go from node 1 to node 4 and then from node 4 to finally node 1, but with 2 and 3 as the intermediate nodes. Okay, so this is now calculated, and what happens? So we find that the optimal tour length is 35. So we got the length, but what was the path? So that is very simple. We will always see here. So from 1, when we were taking the edge, so we find that C12 going from 1 to 2 was the minimum. So here I say that okay, because I went to 2, so this I will have from 1 I go to 2. So this is now fit. Then I will see G2 3 4, which one is the minimum. So I see here I go to G2 3 comma 4. I could have gone from node 2 to node 3 or node 2 to node 4. So I saw there, so this node 2 to 4 is the minimum. So from 2 I will go to node 4. Okay, so this is now done, and from 4 only one option is left, is 3. So the path is 1 to 2, then 4, then 3, and then 1. So this gives me the smallest cycle. So I hope you understand this traveling salesman problem how to solve it using dynamic programming. Thanks a lot. If you like this video, please subscribe to the YouTube channel.